some of you can turn on your video. Ayush, Mohammed, Arpit, turn on your video so that we can discuss better. All right. Who else is there? Sanket, Aniket, Salman. How come you guys are not having your video on? Okay. Mohammed has put on his video. Okay. Shall we start? Today it's going to be very simple. We are just going to have just two concepts that I'll discuss with you about. Okay. One is about small deformations, dealing with small deformations. Okay. I may continue that a little bit in the next class also. But one is to do with small deformations. The other is to do with how do I distinguish those in which I use only equilibrium equations and those in which I need additional conditions. Okay. I'll explain to you along the way. Okay. Is the board visible to you? Yeah. Okay. So let me start with something that is simple. What did we discuss? We said, okay, if I have a rod, okay, of length L, and let's say elastic modulus A, E, and area A, and if I pull this with a force F, it will elongate, let's say by delta, and I have the relationship as delta equals FL by EA, correct? How did I get this? I did two things. One is I had stress, which is F divided by area. The other was strain, which was taken as delta by L. So far, okay? So far, okay? Now, sigma equals F by A, which means I'm introducing a geometric parameter A over here. Epsilon is equal to delta by L. Delta is the elongation and L is the geometric parameter. Okay. Now, on the buzzer, I'm going to ask you a question. On the chat box, I'm going to ask you a question. Okay. Let me see if I can have the chat box on. Okay. Chat box is on. Room is a little crowded. No, I didn't understand that. What do you mean by crowded, Mohammed?
At the moment.
It's fine right now. You can carry on. Hello. Oh, you mean your place? Okay, okay. Sorry. Yeah. Go ahead. Now, are you able to see this? No, it's difficult. No, so I'm going to use my shirt as the background. You are able to see a length L, let us say. Okay. Now, if it elongates by a certain elongated distance, then I take the elongated amount divided by the initial length, right? So far, okay? All right. Now, listen to me very carefully. This length is L, okay? Let's see if I can use a ruler. Yeah, okay, let me use a ruler. Give me a second. This is easier for me to explain. Okay, so I have the ruler now. I have the ruler, and right now what I have is, are you able to see now? Yeah. It's roughly about half the, about one, almost 40% of the scale. Okay. Now I extend it by a certain extent, let's say 2 centimeters. Okay. So I initially had, okay, this is only 1/3. So I initially had 10 centimeters or 100 mm, and I elongated it by about 2 centimeters, which is 20 mm. So the strain is equal to 20 divided by 100, which is 0.2, right? Or in other words, strain is 20%. Okay. The elongation has happened such that it is now elongated to a length which is 20% more than the original length. Okay. All right. Now the trick question. I have now started with 10 centimeter. I have now stretched it to 20 centimeters. Okay. What's the strain now? Yes, 1 or 100%. Okay. Supposing I did this way, let us say I started with 10 centimeters or 100 mm. I now increased it to 15 centimeters, found out the strain. Strain would be how much? 0.5. Now, from this as the reference, I'll now increase it to 20. Okay. So initially it is from 10 to 15. So the strain was 0.5. Now I take 15 as the reference. From 15, I go to 20. What is the strain? Right, 33%. So the total strain would be 50% plus 33%, which is 83%. But if I take this and stretch it to 20 centimeters from 10 centimeters, I get the strain to be 100%. Where is the discrepancy? What is happening here? Very good question. Can I add the strain just like that? Very good question. Okay. There is a change in reference. Okay. All right. So how do I now find out the total strain? That's one question. I'm going to come to that later. What do I understand by this? Supposing I say that I should be able to add, just as Chaitanya has asked, I should be able to add, supposing there are two deformations occurring, one followed by the other, right? When is it that I can add? When is it that I can add? Let us say it is 100 mm. It is now stretched to 101 mm. And then from 101 mm, I stretched it to 102 mm. Okay. I have strain epsilon 1 and I have strain epsilon 2. Okay. So now the question is, epsilon 1 is there and epsilon 2 is there. When can I add and say this is the total strain? Let's say it's in the same direction. Let's say it's in the same direction. When can I add? That's the question. When the percentage change is very small. Correct, Nisha. Right. So the point here is I cannot just take strains and do arbitrarily unless I now tell you very clearly that the strain that I'm looking at here is such that this delta is very small compared to the length L. Orders of magnitude. Okay. So that's the premise by which we will go by, so that it is possible for us to add the two strains together whenever we get into such a situation. Let's say I have a force that I apply first, let's say F1. And then, so if I split this force into, let's say, first stage F1 and the second phase F2, and then seek to find out what would be the total deflection, okay, using this strain measure. Then I have to make sure that the delta that I get here is very small. Are you able to see it? Yeah, is very small compared to the total length that I have. So if it is 100 to 101 and 102, for all practical purposes, it's the same. So that's why we are saying in this strength of materials class, unless I tell you, we will only be dealing with small strings. So far, okay? Is this clear? Okay. Having said this, let's look at another example and understand how we find small strains in certain other scenarios. Okay. I'm going to erase this. Okay. So I built a small structure over here for you. Are you able to see? So this is a structure. This is one member, this is another member. So I'm going to name them. Let's say this is the support A, and this is support B. And let's say this is the point C. And let's say I'm applying a force F over here. Okay, so far, okay. Due to this force, downward force, let's say it has now moved to such an extent, let us say. So far, okay. Is this clear to you? It has moved from this point to this point. Okay. Now, let us say we know the force. We know the member force by applying simple equations of equilibrium, and got it to be moving to this point. So let us say it has moved from here to this point here. Okay. All right. So this is, let's say, C, and this is C1, just to distinguish between. Now, how do I find out this C1? Let us say we are looking at the extensions of this. Okay. This bar is of length L, let us say, and this bar is of length L. And having known the force and the elastic modulus and area, assuming it's linear spring, I'll be able to find out what would be the extension of BC. Similarly, I'll be able to find out what would be the extension of AC. Right? These two are possible for me to find out because I know these are linear springs and are extended by this. Now, how do I relate these to this deflection? Let's say delta at C. That's the question. Okay. Now, how do I do that? One thing that I will consider here is, if you look at the angle change here, this angle change that we are looking at is very small. Right? This angle change is very small. So we're going to utilize that in our estimation. Okay. So I'm going to tell you this way. This is stretched by an extent like this. Correct? Originally, it was here somewhere. I'm drawing the radius from B. BC was initially like this, and now it has stretched this much, which means that this is delta BC. Right? In a similar way, I can do for the other one. Assume this is radially swinging. Okay. So this would be delta AC. So far, so good. Okay. Now it's the question that I'm asking is, where is it going to? Where is the point going to now stop? Having known delta BC and delta AC, I know the arc that I have made over here and the arc that I made over here should have coincided at a point, and that point is the final point after the force is applied. Yes. The only problem I have is this is a curvature and this is a curvature, right? And therefore, what happens here is I'm looking at curvatures which are like this, right? Like this. So far, okay. Are you able to get a picture of this? Yeah. Say yes so that I can proceed.
Yes, sir.
Okay. Now, what do I recognize here? This length is very large. L is very large compared to this deflection delta BC. Similar delta AC. Similarly, here I can say delta BC is very small compared to the length here, right? And in order to use this, when it is extended to a radius which is length L plus delta BC or length L plus delta AC, I recognize that the tangent that I draw over here, let's see if I have a color. I have some other color. Let me see if I can use that. Let me use this. One thing that I'm now able to recognize is we are not very much off if I take the tangent compared to the curvature in order to locate the final point. In a similar way here, I can take the tangent, this is deflected, and I can take the tangent and say, okay, wherever it has met is the point where the final deflection has occurred. In this case, it's very simple because we have a symmetry over here. So it automatically joins at this point, whether it is curved or otherwise. But if it is a case which is different, it will be much different. Okay. For example, you have to be a little patient with me here because I need to now take this out, put this new stuff here. Okay, just bear with me. All right. So now I have like this. I'm going to now change the structure to something like this. Okay. Remember, it is completely in my hands, so I'm just changing it. Okay. So let us say I have applied some force. I have applied some force, and it has now gone to a particular point. Okay. Let's assume now. Let's assume now that this goes into tension and this goes into compression. Okay. Just assume that for a particular force, I'm not going to introduce forces over here because I'm only looking at definition. Okay. Assume that this goes to compression and this goes to tension. So I'm going to call this as what this is B, right? This is B, this is A, right? FAB is negative. FBC is negative. FAC is positive. Okay. So what should happen now? If I have, let's say this is the initial curve as I swing this AC, it has stretched now because this is in tension. So let's say it has stretched. It has stretched like this. Okay. So let us say I have now reached another radius over here. And I know this is delta AC. Okay. In a similar way, I can do this. This has compressed, which means that from the original radius, which is like this, now it has shifted. Shall I use some other? Okay. It has shifted to something like this. So far, okay. Now I know this is delta BC. Okay. So where would be the final point of this? That's not very difficult for me. I will track this curve. I'll track this curve and I'll track this curve. Okay. They have met somewhere. So I'm going to be a little bit off here. So let's okay. I'm reaching a point over here. Okay. Think of it like this. I've reached a point over here. So far, so good. I know now that C has now become C, let's say 1. All right. It has curved and gone to C1. This has curved and got to same C1. This is under compression. I will draw the same thing over here so that this colored chalk piece is the curvature that each one of these form. Okay. Now I'll do the same principle. Since the length is very high, I now can assume that this curved arc can be approximated to be a straight line, tangent. So I'll take this point and draw a tangent. Okay. In a similar way, I'll take this point and take a tangent. So I'll take this point and take a tangent. Okay. Let's say it has met at a point here. Okay. So let me call this as C1. Let me call this as C1. This is the real point. C1 is the real point, and C2 is the point that we found out by approximating them to be same as the tangent. Okay. So the assumption that we make here is C1 is very close to C2. Okay. Now it's not very difficult for me to find this point C2 because what do I know? This is an arc, which means that this will be perpendicular. Correct? Similarly, if I take this will be perpendicular. Right? What do I know? I know this value. So I'm going to use one more piece of chalk. Do I have? Yeah. Okay. This is one thing that I know, which is delta AC. What else do I know? I know this length to be delta BC. This is delta AC. Okay. Using these two, it is now possible for me to find out what will be the point at C2. This is very simple. Basically, from C, it has now shifted to C2. This is horizontal, which means that the total vertical movement has to be equal to delta PC from geometry. And similarly, I can find out what would be the horizontal movement from C here to C2 here. Right? I'm going to use a multiple. Okay. So this assume is a straight line. I need to find this out. This is delta C in the horizontal direction. Okay. Whereas this this is delta C in the vertical direction. Okay, I'm just putting the two directions here. Is this clear to you? So let me summarize. What we did was we said, okay, the lengths are very high compared to the deflections that or elongations that the members go through. Okay, all these are axial members. Number one. Number two, since the lengths are very high, even if it takes something like this, okay, of course I've drawn it magnified too much. This angle and this angle are small enough. Okay, so two assumptions are made here, that the angles that they make upon deflection are very small, and what else, that this deformation or elongation is very small compared to the length. Okay, so that's all about small deformations. We may make amendments when it comes to twisting, bending, and so on. Okay, but the idea is just this, where arcs become straight lines, the deformations become very small, so that now it's easy for me. If I apply force and it has, let's say, reached this point, further another addition of force, it reached this point. Now I can add the strain due to this and strain due to this to get the total strain in the members. Okay, is this clear? Any questions? Any questions? For what if all strains are small, but overall strain is not small compared to the length? No, remember it is strain, it is not elongation. It is strain, which means that relative to the length. Okay, so if I take a very long one, if I take only 100 mm length like this, let's say it is deflected by 1 mm. If I take, let's say, 200 meters of this and apply the same force, it will elongate it a lot. But the elongation compared to its original length is very small. And therefore, it helps me in terms of making it possible for us to add strains. And this is only true for small strains, mind you. Okay. The other strain where you take the real length is called the Almansi strain. Almansi. Okay, sir. Then what is this strain called? This strain is called the engineering strain. Okay. In center materials, unless I tell you, we'll be only using engineering strain, where these approximations hold good. So for okay, shall I go to the next concept? If you have any other question, you should ask me now. Okay, this is a very important concept. Isn't that just integration? Yes, you're right. It's just integration, small numbers integration. You get addition to be almost the same as the actual value. Okay. Almansi strain, on the other hand, you will go step by step, infinitesimally change the elongation, find out the strain, and so on. It is basically in integration you will do from the original length to the final length. Okay, it is also called instantaneous strain. Okay, reason is you go step by step and say, okay, at each step I will change the original length. Okay, so for okay, this also is used a lot in terms of large strains that the structures go through. They also name it as logarithmic strain, because do that integration, you will get a logarithmic value of the engineering strain. Okay, you will get the Almansi strain. I'm going to call this as Almansi strain to be natural logarithm of engineering strain plus 1. Okay, so epsilon, if I use, it is engineering strain. Assume it that way. Okay. So far, okay. Is this clear? Any other question? Very good questions you're asking. Initial and final position, do we need a if we know initial and final positions, why do we need approximations? Yeah, see, initial and final positions in this particular case, if I'm going to go accurately and spot C1 instead of C2, it is possible for me to do this. But what if it is a complex geometry like this? What if it is a complex geometry like this? For example, I have a force applied over here. Are you able to see this? Sorry. Are you able to see this? Yeah. Okay. Now, here, in order to find out the deflection, it's very, supposing I need to find out the total deflection or the strains on each one of these. It's going to be a mammoth task, right? I'm going to come to a simpler way by which you can do this analysis without going with the geometry that we have explained here. The reason why I've explained this geometry is primarily because I wanted you to recognize that we are going to deal with small strings. Is that okay, Aditya? All right, okay, good. Now, the second concept, okay? The second concept, let me just rotate it this way so that, yeah, all right. Now, let's see if we can solve this. So I'm going to have a rod, an axial rod like this. Let's say this is a rigid rod. Pinned like this. Let's say a load P is applied over here. Okay. And I also have, so this is rigid. So let's see if I can draw this nicely. Okay. So I have something like this. I have now attached a rod like this, and now I'm applying the force P. How do I find? So let's say this total length is something I know. Let's say this is L by 3 and this is 2L by 3. Okay. Now, if I ask you the question, are you able to see this properly? Say yes or no so that I can continue. Yeah. All right. Now, when I apply this force P, and if I seek to find out what would be the force in this member, so let's name it A, B, C, and D. How do I go about doing it? This is simple. Why simple? When I apply the load over here, I can probably remove this rod and instead apply a reaction RC. Now, RC is something that I don't know. There are also reactions over here. But in order to eliminate reactions over here, I can take moment about this. In the moment equation, this is known, this is not known, so I can find out RC. Clear? So simple. This is something that I did in engineering mechanics. Yeah. So yes, so that we'll continue. All right. So now this is simple to solve. What if I have one more rod like this attached in a similar way, let us say. Okay, let's say I know the length of each of these. So L1, L2, A1, E1, E2, A2. The area of cross section, the elastic modulus, length, all these are known about them. Now, how do I solve this problem? That's the question. Okay. What shall I do? Any quick answer? What shall I do? Remember, when I remove this and when I remove this, I'll get a, let's say this is E. Shall I put it as F? Okay. When I remove this BC and FG, I'll get two reaction forces. Correct? I'll get two reaction forces. Let's say RC and RS, but I can generate only one equation by taking moment over here. Any other equation will also involve the reactions over here, which means I'm now adding one more uh, unknown in it. Okay, which automatically means that it is not possible for me, to solve this problem. Do you get it? Right? Do you get it? Assume small deformations, but it is not possible to solve this problem. You agree with me? Unless I resort to something which is to do with more than just equation of equilibrium. So I have one equation of equilibrium, but that's not enough for me. I need to now add something where I now have to seek to find out how these guys are deforming. Or in another way, what I'm basically saying is, sir, don't use this. Why don't you just take this, since you have already told us, let us take this to be springs. Okay. By the way, what is the stiffness of the spring? What is KBC? Quickly, let's see one mark. What is KBC? I've given A1, E1, L1. What is the stiffness BC? Quickly. AE by L. Fantastic. So moment as well as the next one. Two of you get the points. Now, I can do the same thing over here. And this is KFG, right? Now, I know KBC, I know KFG, right? So now what I can do is simple. Let us assume that due to this load, it has now tilted by an extent. Remember, this rod is rigid rod, right? Let us say it is tilted to an extent like this. Okay, let's say this is either this or the angle that we have is theta here. Now it is simple. So let's say this length is L by 3, this length is L by 3, this length is L by 3. Now it is possible for me to find out how much this would have deflected down, how much this would have deflected down, right? This point would have now moved to this point. This point would have now moved to this point. This point has moved to this point. Okay, here it remains as P. In this, having known that this is the deflection that the compression that has gone through, that KFG has gone through, and BC has gone through this compression, having known KBC, it is possible for me to find out what would be the reaction. But that reaction, so the reaction force at C will now be a reaction force in terms of theta. Are you with me? In a similar way here, the reaction force at F, are you able to see it? Is equal to reaction force at F, which is a function of theta. This is not multiplication, this is a function. RC is now a function of theta. RF is now a function of theta. In fact, since the lengths are very long, deformations are small, I can use directly a theta instead of sine theta cos theta, right? And remember, this will be a linear function. It will be a linear function in theta and linear function in theta. So far, okay? Is this clear to you? Once I know that, everything will be in terms of theta, I now can apply equation of equilibrium, right? So I can take moment about A is equal to 0, which will give me, now I can substitute. Shall I erase this and replace it by the appropriate reactions? This is RC and this is RF. Now it's possible for me to write RC, which is nothing but some K, what is this? BC, yeah? KBC times, this is, let's say, L by 3, so L by 3 theta. This is the force that I get over here at RC, right? Times L by 3 and so on. I'll be able to solve since I take this to be equal to 0. Okay. This that I have done here is that I have invoked, are you able to see? Yeah. Invoked God. So God has come to my rescue in order to find out the reactions in this particular case, right? So whenever I'm not able to use equation of equilibrium directly in order to get the reactions, I need to now resort to God. Okay. This, where equation of equilibrium is enough to solve, is called determinate problem. What would be the other thing called? If this is determinate problem, the other one where I invoke God would be indeterminate problems. So for all indeterminate problems, I'll be able to solve, of course, once I know the characteristics of the springs that I have used over here. Remember, all structures, all materials that we saw, all items that we saw are actually springs. And therefore, as long as I'm able to find the characteristic of those springs, it is possible for me to solve this problem. This is the second concept I wanted to introduce. Remember, not always will you get a problem with this determinate. If it is not so, I will invoke God. COP is already invoked by getting these reaction forces. So God only is not enough. I also need COP. Okay. So I use God and COP along with the equation of equilibrium and solve this kind of problems, which are indeterminate in nature. Of course, in certain cases where it is a determinate problem, I need to find deformations. That's very simple because I just need to add the characteristic of the spring that comes about over here and solve it. Any questions? Thanks for your attention. I have completed what the two concepts are that I wanted to cover today. Any questions? Any questions? You can use the voice also. Can you unpin me? Can you unpin Sandeep? Can you unpin me? All right. Okay, folks. So you can unmute and ask questions. All determinate problems are solvable. Oh, you mean all indeterminate problems? The answer is yes, provided the copy is with you. I'll repeat it once more. All indeterminate problems are solvable provided the cop is with you. Okay, God will help, but cop has to be with you. The constitutive property of the material of the structure should be available to you, then you can solve the problem. So remember, we have used three of them: equation of equilibrium, COP, which is constitutive property, and then geometry of deformation. All three put together, it is possible for me to solve. When they did this, the civil engineers of 19th century thought they have just completed solving anything till the 20th century scientists came about and said Newton's laws themselves are in doubt now. Okay, but that's the confidence they got by introducing these two, COP and coordinate. Any questions? Any other questions? Remember, it is also possible to solve. It is also possible to solve these problems. These problems as they are instead of applying small deformations. But it will be complicated. If you desire to do that kind of mathematics, it's heavily mathematical. Well, I've dealt with it for 25 years, so it's okay. Then what we deal with is not small deformation, but finite or large deformations. Okay. And you need to do additional courses later, the continuum mechanics and all those in order to solve this problem. Questions. So I have one question for you before we wrap up today. We said these are linear springs. Here also, when we used this, these are linear springs. Do you think I can use it for non-linear springs? What's the full form of God? Oh my God, you've forgotten. Geometry of deformation. Okay, in this course. All right. To me, God is not existent. So, is this clear? My question now is, what if, until we know, let's say we know the nonlinearity of the spring. Let's say I know the nonlinear property of the spring. I know the nonlinear property of the spring. Can I solve the problem? Exactly. We can use K as a function of elongation, and the equations that we get over here will be a little bit more involved, and that's all. Okay. So once I say nonlinear, it can be inelastic, it can be plastic, as some of you want to say, or it can be nonlinear elastic springs. Okay. So I can solve those problems also in a simple way. Okay. So from the next class onwards, Monday, I think we don't have a class, right? Friday's timetable, I think we don't have a class on Monday. We'll meet on Tuesday. I will also send certain videos that I have made for you to go through different problems that you can solve using whatever we have learned today. One last thing about first assignment 1, it's due in a couple of days. If any of you want to clarify certain doubts, I'll be available from, let me pin my, I'll be available on Friday, which is tomorrow, right? Friday. Shall we say 6 p.m. to 8 p.m.? I'll be available on Zoom. I'll send you the Zoom link. I'll be available from 6 p.m. to 8 p.m. If you want to get some clues on something that you're not able to do. Many of you probably may miss out on certain things in the procedure. Remember, you should follow the procedure properly. Okay, that's very important. Remember, whatever calculations you do, somebody else has to verify when you're an engineer, which means that they should know how you have done the problem. Okay, and for that sake, I need to go through the procedure properly. Okay. Whether you like it or not, others should not dislike it. And therefore, you should do this exercise properly. If everything else is fine, thank you for listening. Have a nice weekend. 3 days weekend is coming. I know many of you would want to catch up. Many of you want to relax, whatever you want to do. Have a nice weekend. Before you leave, probably you can say how you're feeling now.